So hello everyone, we will do this, we'll start the lecture again. So basically this is just a simple example of a ResNet misclassifying a horse in the desert, just mainly because of the background information. So it misclassified it as an Arabian camel only because of its location. And this is mainly the reason of the next lecture, this lecture on model interpretation and interpretable machine learning. We can see the same thing here. What is it called? The horse was misclassified as a parrot, mainly because of the colors and the style of the information. So this is a painting of a horse, and it was never trained on such features before or such style, and this led to degradation of results. What interests us is how did we understand, or how did we understand why the neural network made this error? So once we understand that the neural network made the error of this horse because it never seen a horse in the desert before, we can fix our models. We can improve the results of our models after we understand them correctly, right? And the algorithm we used here is called LIME, local interpretable something, right? So this is a very cool algorithm. We will speak about it in the lecture. And this is just one of the main examples where it's very needed to look into every sample and look into every wrong prediction or right prediction and understand why it was wrong or why it was right. Maybe just a simple motivation about the next week. So these images that you can see here, this side is the reconstructed image of the input. So this side is the reconstructed version of this one. And as you can see, the reconstruction is almost perfect, although when we were training the decoder, the encoder was never, ever trained on the reconstruction loss. So the decoder was only being trained on classification, and still it was extracting lots of information about the style of the image, about the background of the image, about the rotations of the image. And these are the things that make the classification wrong, or that make the generalization of the classification impossible to do. So the idea of domain adaptation, or the adversarial losses that we will be seeing in next week, will aim to kind of eliminate or filter out any information that is not useful for classification. So any information about the style, the background, all of this will be filtered out from the encoder, and he will not be extracting these. Now let's start our lecture and understand how can we see what the model is choosing.
May I ask a question?
Yes.
But you want to say what we have some techniques which help us to force the encoder to not look at the style, surrounding environment, and our stuff.
Exactly.
Like, we have such issues. Okay.
Yes, exactly. So this is the techniques, and so not just is one possible technique. Personally, I've worked on 3 different techniques, and there are like millions of other techniques out there that you can always use, depending on the scenario where you are on. So there are techniques which don't require any additional information about the image. So basically just unsupervised images, and they will clean the encoder or filter out the bad information inside the encoder. There are others which try to take, for example, in cases where, for example, you have images of different races. So for example, you have a picture of a woman or a picture of an Asian person, and you're trying to make sure that your model is not biased against Asian people, or your model is not biased against women or Black people in favor of white men, for example. So these are very common scenarios. And in these cases, you might want to add more information to your images, not just image, but for example, a CSV file with the dataset that describes the content of the images. Now for our lectures. So first part of the lecture will be mainly based on this course, on this book. It's called Interpretable Machine Learning. It's an amazing book. It will explain to you things such as what is interpretability, the scope of interpretability, different interpretable models, easy to use interpretable models, logistic regression, decision trees. We will cover them today. Model agnostic methods such as LIME, which is my favorite, or other methods such as GradCam and stuff like this. They're not described in here, but we will cover them in our lecture. Again, I will send this book. It's very important for you guys if you would like to continue in the field of if you want to continue in the field of model interpretation or maybe better diagnostic or better evaluation of models' performances. Now let's start our sweet lecture, right? Share screen. There you go. Nice. Now I can see the lecture here. Oops. Nice. Can you guys see the screen?
Yes.
Nice. Yeah, one thing I wanted to confirm with you that you guys can see, because I'm not very fluent with Moodle. So you guys can see all of this, right?
Yes.
How? Yes.
You mean in our model or in
Yes,
your?
in your Moodle,
Of
yeah.
course, in our.
In your Moodle, can you guys see this? For example, the recording of the video.
Yes, yes.
You can see the quiz. All of this, you can see them easily in the Moodle, right?
Yes.
Yes.
Nice, nice, nice. Let's continue then. So this lecture is going to be about interpretable machine learning models. The learning outcomes of this lecture will be understanding what interpretability is and what are the different and easily interpretable models, the importance of it, the applications of such methods, and the scope of interpretability and simple models that can help you do that. We will also speak about local surrogate LIME, something like that, which is a algorithm that can be used to interpret any black box model we're using. And last, we will be using GradCam, which is, I think, the most important one of this lecture. So GradCam, we will try to go as much in detail as possible. But what I really want you guys to understand, it's very useful and understand how to use it. So GradCam already exists. You're not going to really, unless you're going in exactly an extension of GradCam, you're not going to really extend it or need much detail about it, but you will 100% use GradCam in your industrial applications and in your research to maybe explain how useful or how to explain your results in research papers and stuff like that. So interpretability. The definition of interpretability is not really something that you can easily find in a book, but there are like two main definitions that people really like to use. The first one is interpretability is the degree to which a human being can understand the cause of a decision. So for example, if you have a deep learning model that looks at MRI scans and says this patient has cancer or does not have cancer, the doctor, in order for him to really trust the results of this of the model, he will need to get some sort of explanation. Why did the model make this decision? If it's an image, probably the doctor would like to see where exactly inside the image that the model saw the cancer. Or if it's in their medical history, can the model provide a small list of conditions? So for example, the model would say, if the patient is older than 15 years old and the patient has lots of history of cancer, then I made the decision to classify this person as having cancer, right? So there are different types interpretability, and there are different outputs of your interpretability methods, right? So in this lecture, we will split interpretability into 3 sections. So we'll start by first, what is it? Why is it important? I would like you guys to give me some examples on why it is a necessary thing to have explainability, and examples where it's not, right? We'll also speak about the scope of interpretability or the different levels of interpretability that exist. I don't really recommend focusing a lot on all 5 of them. Just make sure that one of them is always there in your models, which is understanding why did it make this prediction on this sample. And then we'll just see an example of some interpretable models. These models are decision trees and logistic regression. And I think you will not even need me to present how to interpret these. I will just ask the questions, and I'm sure you guys will answer them directly very easily, right? So this is the example that I was just showing. Interpretability is the degree to which a human can consistently predict the model's result. This is the next used definition of interpretability. And this is the example where we have seen a horse clearly misclassified as a Arabian camel only because of its surroundings. And we can understand that by this green area that is being shown in here. So importance of interpretability. Why is it that we can't just like, we have a model, the model has like accuracy of 97%. It's even better than human beings. Why can't we just say no? Why can't we say, that's it, even if it makes a mistake, it's definitely gonna be better than human beings, so it's acceptable, right? It's an acceptable mistake. But that's not the case. In most cases, human beings are really curious people and they would like to have an answer. So for example, if you go to make a loan application, you don't want to just be rejected directly. You at least want to know why were you rejected. For example, it's very common these days to process the resumes using automatic systems. So basically the system will read the resume and try to match the words inside the resume to the keywords inside the job description. If there is a high matching, then he will suggest this resume to HR, and HR will look and read the resume even further. If it's not, then they will reject it. In these cases, usually it's always good to at least give some feedback to the interviewer and say, we didn't accept your resume, mainly because it didn't contain stuff like your experience didn't contain stuff such as Kubeflow, for example, or Docker and stuff like this. That's why we rejected you. Giving somebody back an answer helps them kind of move on and stuff like, so give them an explanation, helps them improve their situation. So if you are in the loan bank and you were refused just because you didn't have enough money, for example, in your bank account, or your source of income is too low, they would tell you, we refused you mainly because your source of income is less than this threshold or something like that. So these are the cases where it's very important to have interpretability. Other reasons can be, so for example, improving recommendations, as we just said. Another one is, for example, Facebook ads. Now, if you see a Facebook ad that you don't like, or for example, is against your religious beliefs or something like that, you can easily just press on the Facebook ad and see why am I seeing this ad, and then just Facebook will give you some of the reasons why you are being targeted for this ad. So for example, we will say that we are targeting people who are of Asian origins and who are living in the US, and they're kind of into the high-tech work and area. So these are the reasons why we targeted you with this ad. And then you can easily just uncheck. So for example, I don't want to be part of the Asian Americans community who would receive such ads. And this is very important for you, for Facebook, of course, to improve their recommendations, and for the people who are users of Facebook, kind of to satisfy their religious beliefs or satisfy their personal decisions and not violate their privacy. Other examples such as safety measures, detecting biases. So this is, I think, a very important thingy. Recently, or not recently, but I think a year ago, a woman just using the latest iPhone just tried to unlock her phone with literally every single Asian person in her office, and her iPhone unlocked. So basically, the iPhone just doesn't recognize that there are any differences between Asian people. And this is very bad. So detecting these biases against the minorities is very important because like you can face very harsh lawsuits, and Apple lost a lot of money just because of this small bug against Asian minorities, right? Another example could be, for example, bank loans who are targeting minorities such as Black women or Black people who are living in suburbs, so they don't give them loans, even if they have the same criteria as another white man. They're not likely to get the loan. So these detecting these biases is very important, because if you have such biases in your models and your model is working outside, you might face some very serious legal issues. So it's always important to perform a very clear investigation of why your model makes its decisions and understand why it does make its decisions. Another one would be to debug and audit models just so they go to the next stage of deployment and stuff like that. In this slide, we will speak about the scope of interpretability. So what are the different levels, or what are the different types of interpreting a certain model? Algorithm transparency. So this one speaks mainly, just ask yourself the question, how does the algorithm create the model? So for example, we can take simply a highly interpretable model, which is linear regression, right? How does the algorithm of linear regression create the final linear regression model? So basically we have the data, and then we either train it with gradient descent, we just optimize the weights, and then we get them, or the better way, which is to use the form. I forgot that the vector form of the answer directly. So basically you just take the data, and from the data you will extract the point which gives you the lowest error, right? So now we know we have some algorithm transparency. We know what is happening. We know why the algorithm built this algorithm, why the algorithm built the model in such a way. And that's mainly because the data is, and the algorithm's parameters are highly dependent on the values of the data. So if you can change the data, you can easily change the value that led to it, right? Another one would be global and holistic model interpretation, interpretability. So this one is, how does the trained model make its predictions? Simple. Take again the, what is it called? Logistic regression or linear regression model. Can you tell me how do you make inference on a linear regression model using just one sample? So basically you just take the sample values, multiply, add, and there you go. You have your result, right? So this is easily interpretable. In this way, you can easily understand what are the features that really contributed to this. What are the so the difference, importance of the features, and all of this information can be extracted if your model is transparent in such manner, right?
What's different here? What's the difference between algorithm transparency and holistic model interpretability? They sound similar.
Yes,
yes, I have the same like problem. I see no difference between first and second one.
Yes, that's true. So let's say that the first one is about the training phase. The second one is about the deployment phase, or about the inference phase. So the first one, we're only interested on how do we train the model. So just imagine that the model is a black box, right? The model is a black box. We have no idea what the model is. If the model allows you to see what's happening in the training, then it's algorithm, you have the algorithm transparency. If the model allows you to see how it's making the inference, then you have this global and holistic model interpretability feature, right? So can you see what's happening in the inference? How do you make your predictions, right? They're actually all of them very similar to each other. And I think if you just read the book and if you just check the book, there is a chapter on this one. It provides you different questions on each one of them. So basically, algorithm transparency, it would say, how do you build it? And then just give you more examples, more questions that are related to this level of transparency or this level of interpretability. The first one is, how is the model being trained? The second one is, how the model making the inferences, right? Does that answer your question?
Yes, thank you.
Good. Now the second one, the third one is very highly related to the second one. So again, we are still in the prediction area. We are still in the inference area. And what we are interested in is how do different parts of the model interact or make or influence the predictions. So for linear regression, it's very simple. The higher the weight of a feature, the more influential it is, right? So this is easy to interpret the different parts of the model, because the parts of the model are just the weights and the bias, right? So this is easy. The higher they are, the better, the more important that feature is. But if you go to another, to a neural network, for example, and I tell you, how do you interpret node 35 in the 5th layer? Can you tell me that if this node goes up, then this is more of a dog or less of a dog? Can you tell me that this node influences the decision based on the input? No, you really cannot. So it's not something as simple. For linear regression, it's very simple. If the value is high, this feature is very important. If the value is not high, this feature will not be important. But for the other ones, for neural networks, it's very difficult to interpret the values of the neurons. So even though you have the whole neural network laid in front of you, you will not be able to understand what does this neuron exactly do. So this is the third level of interpretability. How do different parts of the model influence or interfere or affect the predictions, right? This is, I would say, the most important. The fourth one is the most important one. It's the thing that you will be seeing mostly in your everyday life. For me, in industry, we only work with this one. So we only had 2 clients who ever asked for interpretability, and all they asked for was local interpretability for a single prediction. Why did the model make this decision on this sample? So for example, again, we say we have a Black woman who just came to ask for a loan. We just rejected her loan. Is it because she didn't have enough money? Or maybe she didn't have higher education? Or is it only because she was a Black woman? So this is
It's because your model is biased to Black people.
Exactly. In many cases, your model is going to be very biased. Why? Because it is heavily related to the data. So mainly banks, when they were collecting their data, they didn't have a lot of data for Black people because there was a law. Black people are not even allowed to ask for loans, right? So now when they train it, the model doesn't recognize that, it doesn't have a lot of training data for Black people, and hence you always try to favor the white who has more data on, right? So this is very important. This is the most important part. Interpreting why the model made a single decision, a decision on that single prediction, right? Or on that single.
Can I ask a question?
Yes, of course, yeah.
So the first one is like we know how and why algorithm works.
Yes.
The last hour is about can we explain the result, why we get such result? Yeah.
Yes. Can we explain why we get only one result?
Yeah, why do we need the first one? Like, why do we need to be able to explain how algorithm works in terms of interpretability?
That's a very good
Do we really
question.
need it?
That's a good question. So algorithm transparency, how is the model being trained? It could be very useful to understand, for example, stuff such as, is it accessing, for example, let's assume that Facebook's ads is not accessing private data, right? If we have algorithm transparency, we don't need to trust Facebook will not violate your rights, right? So
It's like to demonstrate that the algorithm is like a good algorithm which will not reveal your private information and something.
Yeah, this is one example of why it is very important to understand how is the algorithm being trained. Of course, algorithm transparency is very difficult, especially if you have, for example, a company, you don't want to just tell them everything about your model. But at the same time, you might want to tell them some stuff like, we are not using this, we are not using this, we are using this, we are using this. Okay, yeah, go ahead, Ali. Yeah.
Actually, this interoperability actually is low restricted. And for example, in the USA, you have no right, especially banks and financial systems, to not give a loan without explanation. In this case, it's a very deep explanation about why you take this decision. This is why it's a very popular direction, the machine learning for now. But in China, actually, and they call it social rating, is about the rating which were conducted by the big banks, and these banks use their very deep nets to predict it give you a loan or not, and they are not need to explain the results. Actually, they itself don't know why you need to go alone or not, and actually all the Chinese people hate this system, and actually it's with two systems, and we see this interoperability actually more beneficial for clients and for us society.
Exactly, yeah. Because if you know why your loan, for example, was rejected, you can change that. You can improve on the fact that, for example, you had less money or you had less income per month. You can try to improve that and apply again for a loan and get it the next time. But in cases where you don't know anything about how the model is working, that's when you cannot really improve or you cannot really change these facts. So it's very important to get model interpretability, at least for what is it called, for single predictions, right? The next level
isn't for single predictions is based on previous ones.
What do you mean?
I mean, it looks like global model interpretability on modular level to me. No, I mean, it's like holistic model interpretability, but specifically for one result.
Yes and no. Let's see. Let me just think about it. How does the model make a prediction? Doesn't really mean how did the model make this exact prediction? How does the model make a prediction in general, right? So on any prediction, how does it do? For example, neural networks, we can say that it inputs the features, and then it just keeps on calculating these functions, and give you the output. But we don't really say that, for example, we don't say that for this client, this was the reason of refusing their loan, right? So we can say that we make a prediction following this algorithm, but we don't really say for this client exactly how did we make the prediction. You see the difference? So they're both on how do we make the prediction. This one is not client dependent or not sample dependent. This one only looks at one sample. Okay, so it's kind of taking this one and putting it only on one sample. We will understand maybe the difference better when we see decision trees. So global holistic model interpretability would need the whole tree to be visible, right? So you will need all the conditions in the tree to have global model, holistic model interpretability. But in order to make local interpretability for a single prediction, all you need is one branch of the tree that is related to this prediction. So all you need is just the small branch that made this prediction.
Nice example. Thank you very much.
You got the difference?
Yes, absolutely.
Thank you. Local interpretability for a group of predictions. So this is also similar to a single prediction, but instead of focusing only on one sample, we need to do it on a group. So for example, we take the group of Black people and we try to understand why did we make this prediction on these groups, on this group. So basically, this is another level of interpretability. It's always also helpful. They're all kind of similar. So I think the only one that is a bit different is the first one, because it speaks mainly about the training process of the interpretability area. All the others are aimed at the inference, because that's where we need the interpretability the most. The first one is a bit vague. So basically, you are speaking about how the model makes the predictions in general. Then you will speak how individual parts of the model contribute to the prediction, and then you just it kind of focus only on one sample. So we're not focusing on the model, we're focusing on this sample. Why did the model work on this sample? And then we make it on a group of samples, right? Let's maybe visualize it a bit differently. I think we could have something like this. Graph. Not these. Not like this. I will try to make a simple visualization of these, not things like this now. These are not useful. Yeah, Venn diagram like this could be very useful. Sorry. So let's imagine that this is how the model is being trained. This is how the model is being trained. This is algorithm transparency. The other one is how the model makes its predictions. Inside of it, there is how the model makes its, how individual parts of the model contribute to the prediction. And then a smaller hole inside both of them would be how the model makes predictions on a single instance. And then we have a bigger hole that is still inside all of them, just like this, which speaks about, let's say, like this. And then we change the transparency. So yeah, there you go. So here, on a batch, on a single node, how do the different parts of the model make interpretations, make the prediction, how the model makes interpretation in general, makes the prediction in general. And this one is algorithm transparency, how the model makes how the algorithm makes the models. Did you guys get this?
Yes, if you understand how your models works in predicting, you're happy.
Good. So basically, yes, exactly. What we aim is to get all of these. In case we don't get them, so we try to aim for the smallest one here, which is just at least tell me why did you make this exact prediction, and then we try to get the bigger ones, right? I will finish this diagram after the lecture, and I will add it to you guys later. Maybe this will help you understand how the different scopes relate to each other. You guys think it's useful?
Yes.
Yes.
Perfect. Perfect. I really like using diagrams. I don't know why I didn't add a diagram for this one. It's definitely a place for a diagram here. Anyway, let's just continue with the next slides. So logistic regression is the best example you can have for an interpretable model, right? So let's ignore the first. So for example, we said, how do we make the predictions? How do we make how the algorithm makes the model? We said by the data, and then from the data we just fill in the formula, and that's it, right? The second layer is how does the trained model make its predictions? Again, we said is logistic regression takes an X, multiplies it by the weights that it has, and then it gives you the Y. So we have that second level of transparency. How do the different components of the model make the prediction? In this case, I would like just to remind you guys what is the different components of logistic regression formula. So I think you guys all remember that logistic regression, in reality, the model itself is only this, right? Yes, the model itself, or the parameters of the model, are these, B0 and B1. This is the model. This is your real model. See, B0 and B1. How does B0 and B1 influence the predictions in general, right? So you can say that B1, the bigger B1 is, the more influential this X1 is. And then B0 influences the predictions by saying that this is the value when all the other, what are they called? When all the other X's are set to 0, right? So this is the bias. This is how the bias interferes, or how the bias affects the final prediction, right? Now the fourth level, which is why did the model make its predictions on this single instance? In this case, all you need to do is understand. So you have, for example, let's say 5x plus 2. Let's write it down, right? So here it is. So this is our logistic regression in reality. Let's say that this is it. And what's happening here is you can easily tell him how can he change this x, if it was, for example, x2 plus, let's say 3 or 4, x2 plus 2. You can easily tell him how to change his x1 and x2 in order to make, to change the label, for example. So if he wants to be accepted, he can easily just change x by putting more x, or for example, if this was a negative, then we would ask him to reduce his x2 feature and stuff like this. So this is how we do the fourth layer of interpretability. The fifth layer of interpretability is pretty similar, so it's not very difficult, not very different in most cases from just the single one, right? Now I'm going to have to ask you just a small set of questions, and you guys can tell me. For numerical features, how are they being interpreted?
One more time, we're saying about the logistic regression in this case, yes?
Yes. So if you have a numerical feature, how can you interpret this numerical feature based on what you have in the model, right?
What is the input, picture or what?
No, it's just an x, just x like this. For example, the height.
I think it's the same, just numerical feature.
Exactly. So kind of what we just described right now. So what we have described was how does numerical features influence logistic regression. In this case, numerical features are influenced, or they are influencing only the part where they are multiplying with their corresponding weight. So every every numerical feature has a corresponding weight. If you can interpret that weight, then you can easily interpret what to do with this numerical feature. Binary features are kind of the same, but in this case, it's not whether it goes up from 1 to 6 or from 1
like
to minus 5.
1 and 0 turn on.
Exactly.
Turn off.
So either you are, for example, white or black. So this is the kind of feature that we have. And how do we interpret it? Just by setting it to 0 or 1 and seeing what happens, right? Categorical features. For stuff such as logistic regression, he doesn't really understand what categorical features are. So what do we do before going to categorical features? Yes, so we either convert them into a numerical feature or we convert them into a binary feature, depending on whether they are ordered or not ordered. So basically, are they nominal categorical features or ordered categorical features? I'm sure you guys already know the difference between them, but can somebody give me what is the difference? What are the different categorical features that you understand?
Ordered are like large, X large, and small. And
yes,
nominal is colors, for example. Like
exactly, this is the perfect example for it. So if you have something like the size of the t-shirt, for example, you can easily take it from large, X large, and small to like 0, 1, and 2. Yeah, so you can convert it into a numerical feature, and it still will maintain all of the what are they called, the information inside the categorical feature representation. And if you have something else, like for example the colors, or for example the name of the animal, so we have animal, we can't say that cat is number 1, and then mouse is number 2, and then dog is number 3. So we have now this order that doesn't really exist in the feature. And in order to eliminate it, we must convert this kind of categorical features into binary features. So basically a set of binary features, right? So this is how we interpret these. For the bias, I already said how do we interpret bias, but can somebody tell me again?
It's what if our data is equal to 0?
Yeah, the bias, how does it really influence the model, or how is it used for making a prediction on a single instance?
Starting point for our predictions.
Yeah, you can think of it as the starting point, or as the point when all the others are set to 0. This is like the value that they get by default, right? Next, we will speak about decision trees. So let's take, for example, this as a decision tree. Let me get a bigger decision tree, right? Just so we can see what decision trees are, and then we make the decisions from them. No, I think I like this one. Nice, right? Nice. So how do you explain a? Let's go through the levels. So the first level, how does the model make the how does the algorithm make the decision tree? So we all know how the algorithm training of decision trees is, and we basically start by from one feature, split on it, then the next features, then the next features, and then calculate the entropy and trying to reduce the entropy by splitting them, right? The second thingy would be how does the model make the inference? So in this case, we all know that we just take any kind of sample and we forward it following the different conditions, right? The third layer of understanding or third layer of interpretation of a model is how do the different components interact with the predictions. And in this case, the different decision stumps are what splits the decisions splits the samples from going in one direction and to the other. So we already know how do these individual parts make this thing. So if we can just say, the first one is if the client is taller than 2 meters. The second, if the client is smaller, or if he is thin and stuff like that. So
if client is taller than 2 meters, then you will not give him loan, yeah?
Yeah, exactly, because he's too tall. He doesn't deserve. So we already know how these decision stumps influence the final decision. The third layer, the fourth layer, which is how does it make a single prediction? In this case, we just follow the if statements, and whenever whatever the if statement takes us, we land in that area, right? Yes, another one. How do you measure the importance of features? No.
So maybe the higher the feature decision tree, the higher importance it have.
Exactly. So there are different models. I'm sure you have known something called as feature selection.
Yes, of course.
Actually higher, but is this feature possible to split on like more balanced classes? Like
exactly. Yes.
Then it's a more valuable feature.
Sure. So basically, it's definitely going to be a formula based on the decision tree. We look at it. Does this feature help sort out the different or reduce the entropy inside the decision tree? If yes, then it's very useful. If not, then it's not very useful. Another question would be, how can we change the class of a prediction? So if we say, this is the reason why you have been diagnosed with or how you have been rejected. How can we make this reason disappear or change to accepting, for
example? Delete the node that did this or change.
No, we need to change the input, right? So we are trying to tell the client, yeah, please make more money or please reduce this, but we need to give him the reason, right? So for example,
we just tell him like in the tree, it did this, and you need to change one of them.
Let's say, for example, in here, the decision was not to give and the decision was to give. The easiest thing he can do is just change this condition, right? So if his case changes this condition, he will switch to the next one, right? If not, then what we can do, we can propose to him to maybe change this condition and go in this direction where he would get the loan. So this way we can give him like recommendations on what can you change in order to get a different class, or what can you change in order to get better response from us. Is that understood?
Yes.
Nice. So now we have spoken about concepts such as what is interpretability, why is it important, what are the different levels of interpreting a model, and what are the different smaller or simpler interpretable models that exist. There are lots of other interpretable models, but what we are really interested in is not interpretable models. So we're interested in things that are difficult to interpret, which are, for example, neural networks and CNNs in our case, right? So for this, we need to use another set of algorithms, which are called model agnostic explainers. Model agnostic interpretability. We got to this realm of interpretability. There are different techniques for this one. In the book that I just sent you, I think they describe around 7 or 10 different interpretability, or what is it called? Model agnostic interpretability methods. The best one that I found was LIME. It's the easiest to use, and it has lots of implementations already out there for both for tabular and works for text and works for images. But I find that it doesn't work better than GradCam. So soon we will speak about GradCam and why is it better for images. LIME in simpler terms. LIME in simpler terms, what it does is just takes a very complicated model and tries to estimate it locally, only in this decision, tries to estimate it using a simple.
Bless you.
Thank you.
Bless you.
Bless you.
Thank you. And tries to estimate the decision made only locally, only in this area. Tries to estimate the decision in this area using a simple model. So as you can see here, using a simple linear model. And this, in many cases, is very doable, because it doesn't matter how non-linear your model is. If you zoom in close enough, you're always going to find a decision boundary that is kind of linear. So that's where the idea comes from, right? That we can estimate or we can approximate any complex non-linear model on a very local area using a simple linear or interpretable model. So this is where the core idea comes from, right? It's very important to check the sizes. So basically, we're interested in this point. We want to understand why did our very complex, highly nonlinear model make the decision of this point to be positive and not negative. So you can see here, what we did is we sampled some points inside the data set randomly, and we attributed weights, right? So you can see that points which are close or very local to our prediction, they have high weight, and it's represented here on the size. And points which are very far from our point or from our point of interest are usually just attributed very small weight, right? After that, we simply create a simple linear model by using or by attributing the weights that we made, which are dependent on the distance between the target point. So for example, here is the model. We give it these points with high contribution to the loss function, and these very far points to be small contribution points, right? The decision boundary that was made looks like this. Let's try to draw it a little bit, just to understand. Yes. So basically what the model says, what our LIME says, all of this is the black class, or this is the blue class. This is how we estimate using our LIME, right? And all of this is the positive class. So this is the decision boundary of our new LIME. It does not at all coincide with what the complex model is on a global manner. But if we look only locally, it is kind of similar, right?
It extracts most important features and using them to build linear regression.
Mm-hmm. Most important what? Not features, most important samples.
Samples.
Yes. Now, okay, sorry, why is this? This is a very important one. Very important image. We need it. okay, I'll fix this very quickly because we really need this image to understand the model. And for some reason, it's not loaded. I think I'll just restart, right? Shared screen again. Yep. There you go. So everyone can see that this is not a linear decision boundary, right? This is not a linear model. This is a highly complicated model, which makes this shape, right? And what we are interested in making or understanding why the decision of this point was made to be green or gray, right? Why was this point attributed to the negative class? So what we do is we take this point, sample out a very large amount of data. This depends. Sometimes they sample out 10, sometimes they sample like 1,000, 10,000, however you want, right? And then each one of these samples will be attributed a weight according to its distance from our target or our instance of interest, right? After this, we create or we build a linear model based on weighted linear model or simple weighted linear model to do the classification. And you can see here how the threshold is, right? So this is the decision boundary of Lime, where all of this is the minus and all of this is the plus, which is not, again, which is not representative of the true function, but in locally, it is representative of it. So once we have this decision boundary, very linear, very easy to interpret decision boundary, then we can start making the previous, what is it called? Using the same methods of interpretation that we used before to understand what are the features that led to this decision, or what are the what things can we do to kind of change this decision. So all of these things can be done after we build this new simple linear model on a local manner, right? So just to go through the steps again. So first you select your instance of interest, randomly get some more points and make their predictions, weigh the samples according to their interest, according to their distance or their proximity to the instance of interest, train a weighted interpretable model on the dataset with the weights or the variations. So these are the points that we will be using for training. We will not be using real data. We will not be using real samples. We will be using generated samples. Okay, so it's very important that we will not be using the training data. We are going to use a generated or synthesized data set. This is very important because it will make the difference between Lime for tabular data, Lime for textual data, and Lime for images. It's
how it's gonna work with images even?
Yeah, we'll speak about that. So the only difference between Lime for tabular data, Lime for text, and Lime for images is how or the method of generating this random data samples, or these like this, what are they called? We call them the variations, or well, yeah, these random points that we will be using to create our model, right? Train the weighted interpretable model and then explain the prediction by interpreting the local model. So basically we interpret the big model using the interpretation of the smaller model. And this can only work locally. It doesn't work on, so for example, if you try to take the same model, but put it on another area, it's not gonna give you correct performances. It's only going to give you performances for this single image. For this single instance, or for this single, for this single sample. So again, Lime is done sample-based. So basically, if you would like to interpret a lot of samples, you're going to have to retrain Lime for each one of them, right? Now, how do we extend this framework that we just described to not just what they call, to not just tabular data, but to textual data? The main difference is the following, right? how can we generate random text, right? And how can we measure the distance between a text and another? And the last, how can we train a linear model on text? So these are the questions that we'll have to answer in order to apply LIME on textual data. It's very simple, right? So we take, for example, this sentence. We try to understand 4 Christmas songs, visit my channel. So our goal is to apply spam detection on a series of text. This one was predicted to be a spam. Why was it predicted to be a spam? This is why we could use LIME for textual data, right? So here we can simply give information to people who are making mail and stuff like this to kind of structure their emails in a format that doesn't make them look like spam, right? So what we do is very simple. First, we try to represent this this text as just a vector form, right? So basically, we have a vector form for Christmas song, visit my channel, 1, 1, 1, 1, 1, 1, 1. And then we just randomly remove some of these texts. So for example, let's say for song, visit my wink. Here, for visit my channel wink. Another one is Chris, so 4 is deleted. Christmas song, visit my no channel and wink, right? So these are the different data samples that we'll be using. So these different black points in this area, right? Generating different text by removing words is the way that we will be creating our samples. Now you can see that in this representation, so we have 1, 0, 1, 1, 0, 1, 0. So this is no longer text. This is a vector form, right? So this is easily trainable using linear models. You can see their probability. Yes, their probability is not, in fact, what is it called? It's not their class, but this is the output of our real model, or our model that we're trying to interpret on this sample. So we give it a sentence saying 4 songs, visit my and wink, and he will say this is a spam with the probability of 17%, right? The weight is just as before, so it's kind of the distance between this text with our original text, and it's simply a function of how many words have been removed from the sentence. So for example, we can see that this one was only 1 removed, so it's 86. This one had 3 values removed, so it's smaller, smaller weight, which means it's much more distant to our original image, right? To our original text, right?
So if we're testing one sentence, we are generating for LIME these fake sentences, and
yes.
They based only on this sentence or on other ones also?
No, only on this sentence we generate the fake data set.
Also, we're normalizing weight for this specific sentence or not?
What do you mean? The normalizing the weight for the distance?
Yeah, I mean, if we have all words present, it's going to consider it 100 weight.
Yes, 1. It's going to be 1. And if we have 0 words present, it's going to be 0.
I understand. Thank you.
You're welcome. After we get this, what do we do? We simply train a linear model, right? So we simply train logistic regression based on this new numerical features, right? We don't have text anymore. We only have a vector of 1, 0, 0, 1, 1 and stuff like that, and a weight and a class. You can consider this as your label, right? You can train logistic regression with this label, sorry. And this is the output of LIME. So here we have the feature and the feature weight. You can see that most of them were 0. They have no feature weight, but the word channel is like very high in what is it called? In the sorry, in the spam detection. So if you use the word channel, you're going to be most likely detected as a spam. Why? Because usually YouTube channels and I don't know, stuff like that, they always just try to spam you with new content and stuff like that. So that's why Lime takes the word channel, or predicts that the word channel is very influential to becoming, or to giving you spam detection, right? So do you now understand how to use Lime, this simple idea, on tabular data and textual data, right?
Yes, very
Nice.
beautiful expansion.
Before going to the next area, or the next side of explanation, which is Lime for images, we need to speak about something called superpixels. So superpixels are simply, we take this image and then we represent it like this, right? So superpixels are interconnected pixels with similar colors. So we can see that this area, or this area, looks kind of similar, right? This area, although they have different pixel values, they're very close to each other. So we can consider this as just clustering of pixels based on their colors and their location in the image, right? So you can see here, these are the superpixels, different superpixels everywhere, right? So do you now understand what superpixels are?
It's like a blurring, actually.
Yeah, exactly. So
You
it's very
join
similar
several
to blurring.
pixels.
Yeah, it's very similar to blurring, and it can be used as a technique of data augmentation, right?
Yeah.
Nice.
It's like with like it's a min sheet of some kind of like categorization of
Yeah,
pixels.
exactly. Now let me just show you something and ask you, how would you convert from an image like this, using the idea of superpixels, and generate data in the following manner that has like vectors, right? Can we make a vector called superpixel 1, superpixel 2, superpixel 3, superpixel 4, superpixel 5, 6, 7, and then just turn off this superpixel or turn it on? And like this, we will be generating our new data, right?
I was thinking about the idea what we may make a like a little superpixel, or maybe like make this pixel bigger and bigger, and by this like create a weight. It's like was the idea, or is we wrong?
Can you describe it again?
For example, we can make a really small superpixels. For example, we just like take one, for example, 100 part of a picture. Maybe make this superpixel bigger, bigger, and bigger, and bigger with superpixels where less of weight with this picture in.
Perfect. This is a great example, and this could be as another algorithm for making Lime, or applying Lime on images. It could be even better, right? So from here, from what currently is being done, so basically we generate something very similar to this, but instead of the text or the words in the text, we will put the superpixels. So here we have superpixel 1, superpixel 2, superpixel 3, superpixel 4, and you can see we have them. The number is pretty limited here, and we either turn it on or turn it off, turn it on or turn it off, and this way we generate new images, or this way we generate random images, right? And populate our sample.
What means turn on and turn off? It means like to be black, or
like
to
this.
be like.
So basically,
like you are not using them for predicting.
Yes, you're not using them at all. So for example, you just remove this area and send it through the model, and it will give you whether it was classified or not. Nice. So after you have this data set of just ones and zeros, and you have the probability.
Can I ask a question?
1 second, just let me finish. Yes. So basically, you have a new data set of ones and zeros. You have the probabilities, you have the weights. You just train your logistic regression, and you will get the following. So what you will get is, instead of the word here, you will say superpixel 1 has feature weight like this. Superpixel 2 has feature weight like this. Superpixel 3 has feature weight like this. The higher the feature weight, the more valuable it is for contribution. So for example, we come here We generate different instances, right? And then we say that these superpixels are useful or not for the explanation, right? So this is the explanation in reality. So the explanation is only the amount or the group of superpixels that gave us the good results. So you can see here, this is the group of superpixels that gave us the precision in this case. If we go back to the first example in here, this green area is the group of different superpixels that contributed most to the decision of the neural network.
Interesting. Thank you.
Thank you. Did somebody have a question?
Yep, I have.
Yes.
We are creating like augmentation of the data and put it to the original model, yeah?
Yes.
Some kind of augmentation.
Perfect. Yes.
But
We're
for
creating
this, for example, for this concrete image, here's a frog with a heart. And which is the principle we're using to make like augmentation of this superpixel?
Yes. So we make the superpixel distribution like this. So we cluster them like this, right? So this is the clustering that we get. And then we remove coupled superpixels. So we remove 5 superpixels, for example.
But for example, on this picture, we can remove like all green and it will be only like a hair, and we can make a wrong prediction.
True, that could happen to have a very big superpixel. So it depends on the algorithm you are using for making superpixels. There are lots of algorithms, and they can help you make some constraints. So for example, you would say superpixels should not be too big that they consume, for example, 70% of the image. Yes, okay, and they should not be too small that they are really worthless. So it depends on your algorithm for creating the superpixels. You will have different results.
So we use original model to create a prediction from your data, yeah?
Yes. So as we did here, we used the original model to make these predictions of the blue, blue and minus, right?
And Lime is used to create like the augmentation. No, not like, but some kind of augmentation and explanation. Like if we change this, then we get another prediction.
Exactly, yes.
So it tries to explain in such a way.
Exactly. So it tries to explain to you why did we make this prediction. In this case, the explanation was the face of the frog. Because of the face of the frog, we made this decision. Lime also doesn't just give you the positive reason, it can also give you the negative reason. So for example, if you have a feature with the minus value for a parameter, for the parameters of logistic regression, that means this feature was the reason why we went for the negative class. Okay? So you can interpret why did we choose the positive class?
Has a negative weight, then can you explain again?
Let's see. So for example, logistic regression. We have a feature called age, another feature called height. And we are trying to predict the I don't know, whether this person...
Wait.
Huh?
It's in your suggestion. We're trying to predict.
Yeah, we're trying to predict the weight. For example, after we finish, it turns out that weight equals 100 plus, let's say, plus height plus 0.8 times height minus 5 times age. For example, age, the older you get, the shorter you become. For example, I don't know. So this is an example of scenario where the value of the feature or the value of the parameter of the feature is negative. You got it?
Yes, thank you.
Nice. So sometimes the values of or the features of logistic regression and linear regression can be negative, and that means that that superpixel in the case of images or that word in the case of text was the opposite. So it was contributing to predicting the opposite class, right?
any techniques. I mean, if for example, training our data and using super pixels to picture augmentation, it can affect performance of Lime.
Yes, of course. All the hyperparameters that we are talking about will influence the Lime. So, for example, how many samples will you generate? This will influence your performance. This will influence the speed and the performance. The weights, usually they're defined. The training, for example, if you're going to use logistic regression, what kind of optimizer will you use? Remember, there are 3 optimizers for logistic regression. This can influence the final result. There are different hyperparameters. For example, for here, let me think of a hyperparameter that could influence. I don't know. I think this is it. So basically, taking or not. Another one in superpixels would be the superpixeling algorithm. This is a very influential hyperparameter, and it will change the results of Lime drastically. Did that answer your question?
Yes, thank you.
Nice. We will go to the lab. We will see that it's actually a very simple function call that doesn't really take you a lot of time. So basically, as long as you understand how this model works, where can you use it? Using it is just pip install Lime and then wrapping your model inside. So it's very basic stuff.
Where Lime can be used?
So it can be used in images, text, I don't know, maybe videos. If you can find a method to sample or to create new videos, to create random videos, and a method to map these videos into a vector form, then you could easily use Lime. I would say also audio. If you can take audio, maybe audio, you can just make...
Can't we just use the same method?
Yeah, we can. We can use like superpixels for
superpixel with that, and it would be like 3-dimensional.
True.
Thing.
And we can also do, yes, we can do that. Superpixels and 3-dimensional space, that's very doable. Yeah, that's doable for videos. Another one for audio, also, it could be doable to split the audio into 1 second, right? So basically, second 1, second 2, second 3. And this is your, well, this is what we are using here as superpixels. Well, these are your features, right? Every second is a different feature. And we say whether this feature was useful or not. So this is completely doable also for this kind of data. I don't know what kind of model, because really it does work in all cases where you can generate new samples and map the samples into a vector form. Was that understandable?
Yes.
Perfect. Now, what we have seen so far, we have seen interpretability, what it is, and how it's done, the importance of it, the scopes of it. So we have seen 5 scopes. We've seen the first one, algorithm transparency. How does the model create? How does the algorithm create model? The second level is how does the trained model make the predictions in general? How does the third level would be how does each component of the model contribute to the predictions? The fourth was how a single prediction was made, and then how a batch of predictions was made. So these are the different scopes of interpretability. We've seen what are some of the examples of interpretable models, such as logistic regression, which is the most important, and decision trees. Also, we've seen how it's done. We have seen what Lime is and how can we use it. How can we use this concept of using a simple model to explain a more complicated one on a very local area. And we've seen how can we apply it to tabular data directly, and how can we apply it to text and images by simply converting the text and the image into a set of vector form features that can be turned off and turned on again, right? So this is what we have seen so far. The last part of the lecture would be on GradCam. Yes, we have not enough time. I hope that the people who will be leaving soon, just please finish the GradCam part, and you can leave very quickly. So GradCam is a very popular technique for creating class-specific heat maps based on a particular input image and a trained CNN and the chosen class of interest. Let's just go directly into the code, and I will get back to it again. So this is what we mean with a class-specific heat map. So we give it an image. You give it neural network that is a differentiable neural network using CNNs, and it will give you this feature map or this heat map that tells you, I made the decision that this is a dog because of this area. And then when you just map this heat map on the image, you will see that the face of the dog was the reason why we made it, or we classified it as a dog. So this is what GradCam does. In simpler terms, so basically it tries to back propagate only this. For example, we have tiger cat in here. This class, we try to back propagate it through the fully connected layers into the feature maps of convolutional neural networks. So here we have the back propagation, but not all the way back to the image. No, we only have it for the feature maps. So we have a set of feature maps in here, and then we have their back propagation or their gradient. How do they influence the corresponding class? So how do these feature maps influence the corresponding class? And then we just combine all of them, all of these feature maps based on their influence. So basically or based on their gradient. This feature map influences this class a lot. So basically we will have it, we will give it a high weight. This feature map doesn't influence the class, so we give it a low weight. And then we just take the mean of all of these all of these activation maps. Bless you. So we take the mean of all of these activation maps weighted using their gradient or their influence on the class. And this gives you this gives you this heat map. In reality, this heat map is just it's just a combination of all of the feature maps of the convolutional neural network, right? So we just combine them using weights. These weights are calculated based on their influence or based on their gradients towards the specific class. So again, yes, I just want to finish this section quickly so that the guys who can leave soon can leave, and then I will go back into it in detail. So the steps are in general, we compute the gradient, so we compute the gradient of the YC, a certain class, with respect to the feature map activations AK of a convolutional layer. So basically we compute this gradient. We calculate the alpha by averaging the gradients. So the alpha is basically how does this how does this feature map contribute to this class. So basically we calculate these alphas based on the average pool of the gradients over the width dimension indexed by y and the height dimension. So basically this gradient will give you a matrix. It's not going to give you just one value. So basically we just take the average pool of this matrix and we get a alpha value, which is representative of how does this feature map activation influence that class. And then using these weights and the activation maps, we just merge them together and we get our final heat map. For those who want to leave, you guys can freely leave right now. Technically, we have finished the lecture. I know that you have a meeting right now at 2. So basically, the rest of the lecture will be just a simple example of code, how to do GradCam, how to do these things. It's very simple code. You can easily understand it, and the recording will be up later on. So it shouldn't really influence a lot on your understanding of the rest. Just as long as you understand that GradCam creates you class-specific heat maps, and it does that by backpropagating the influence of each feature map onto the class, right? Yes, so again, if you guys want to leave, you can leave. I see that 2 people have already left. Oh, again, this picture is not here.
Okay, so
let's yes, let me maybe represent GradMap slower a little bit.
Yes.
And then if you guys have some questions, please go ahead. So GradCam, again, is from, in my opinion, the best way to understand why did a convolutional neural network make a certain prediction. Although Lime is very useful, Lime is very performant, but as you can see, Lime in here, it's very dependent on these superpixels. So basically, if there was a pixel in here that is contributing to making the class higher, and a sample in here that is making it, the rest of the samples are making it lower, then Lime will not be able to detect this area. So we will be aggregating all of this area together. So this is bad. Whereas GradCam has more flexibility over the image. So as you can see, the shapes that they give you are not very super pixelated. So basically every one of them is useful in a manner, right? So it gives you this heat map, and the hotter the color, the more influential that pixel is for making the prediction, right? Just again, I will describe this quickly and ask you a simple question. And after we finish, I want you guys to answer me this question. So we have, yes, so we take the feature maps from the CNN, right? And then we calculate their gradient to this specific class. So say we have this class that your cat, or we have another class called a dog. The weights or the gradients that we will be calculating will be matrices. So what we do, we just take the average of each matrix like this and convert them into a weight vector, right? So this weight corresponds to the first activation map. This weight corresponds to the second activation map, right?
Activation map, you mean what?
Feature map.
Ah,
Yeah, you see, after every layer, we get an activation map, right? After every convolutional layer, we get a feature map. Do you know what feature maps are?
Yes.
Let me just show an example of what feature maps are.
Do we take feature maps from each layer or from last layer? Or
That's a good question. So according to what I've seen, we only take the ones from the last layer, but there is not really, I don't really see any objection against taking lower level, what are they called? Lower level feature maps. But since the final layer is usually what contains the bigger picture, is usually the thing that contains most of the information about the image, right? So easily you can take the feature maps from all the CNNs, for example, upsample them all to be in the same size. So basically all the feature maps have the same size. So you can build the same size feature map, right? And apply the same algorithm. I don't see a constraint that doesn't allow you to use the other activations. The authors of the GradCam decided to go with the final layer, but you can choose to do whatever you want, right? So for example, if somebody wants to do research, you can try this one. I just want to show you guys what is an activation map. 1 second, just for people who might not be very comfortable with the term. 2D visualization, right? 2D. Wow, I have so many things here. Yeah, 2D visualization of convolutional. Share screen. There you go. So these are basically the activation maps so far. You see, these are the set of feature maps of the first layer, set of feature maps for the second layer, a set of feature maps for the fourth layer, a set of feature maps for the final layer. What we do with GradCam, we take only the feature maps of the final layer, calculate, can I do something? Yeah, so for example, this, you see, calculate this backpropagate the value of this y, so for example, class number 7, onto all of these different feature maps for the last layer. And then using this resulting matrix, for each feature map, we will have a resulting matrix. We just take the mean of this resulting matrix and consider it as a weight for the activation map. And then we combine the activation maps together with multiplied with their corresponding, let's say, alphas, which are their corresponding influence, right? Which is their corresponding influence. And then we send them through a ReLU activation function, just so that we don't have a negative value over there, right? And that's it. There you go. You have your GradCam. So this is a GradCam. There is another one called as guided backpropagation GradCam. I really don't recommend using it. It doesn't give as good results as GradCam. So it's basically an extension of GradCam, but through what I've seen, it doesn't really give better results. It usually gives worse results than GradCam.
So it's looking on deeper layers, right?
I didn't hear you.
So it's guided backpropagation is looking on more deeper levels, right?
True, exactly. So basically, it doesn't look at the layers, it looks at the image. So basically, it calculates the backpropagates all the way back to the image values and says that this pixel influenced this class high, or this pixel influenced this class low, and then they just combine both methods. I don't really like the results that come after the combination. So I don't recommend you guys to go through guided GradCam or guided backpropagation. Focus only on using GradCam for now. Maybe in the future there will be some sort of improvement.
I may say what why is guided not working, because actually yesterday we discussed about the main properties of convolution nets. And convolution nets are about to understand not one pixel but a group of pixels in their order. And actually, from your explanation, it seems like guided backpropagation just put all your attention to separate pixels, and I think it's wrong in the origin. This why it's work bad. It's not like about the convolution and how it works. It's like it can explain the work of convolution.
True, it's not bad as you can think. So if you come here, so you can see that guided backpropagation definitely kind of highlights the dog and the cat. So it's definitely doing something. But if you can check here in guided GradCam, we're only focusing on the tiger cat. We don't care about the dog. Guided backpropagation shows you the dog. A GradCam only shows you the cat. You get it?
But okay, it shows the importance of the pixels, but what convolution that shows the importance of the features, and
Yes.
everything is different. Is difference.
I didn't really get. I might not have gotten you correctly, but I think you are correct at what you're saying. Yes.
Okay.
Just to go through this again quickly. So we basically calculate a feature map or calculate a matrix for every activation map in the final layer. And then we calculate the alphas of the gradients, or which are, we calculate the alpha of every activation map based on the gradients that we get from the first step. This alpha is just the mean, complete mean of the gradient matrix, and then we just combine matrix, multiply it with a value, and then just sum all the matrices together. Now the question is, here you can see that our dimensions are big, right? But the activation map of the last layers are usually very small. So in reality, GradCam gives you the size of this, right? How can you convert a heat map this small to fit an image this big?
Automatic orders.
No,
transpose
this is
convolution.
Too complex.
Transpose convolution.
Correct answer, very correct answer, but the complex answer. So this is the complex name of the operation. I want the very simplest name possible for the operation. It's the same operation you just described, but simpler.
There are two good answers in the chat.
Deconvolution, you mean?
Yeah, it's simpler to deconvolution, but simpler. Upsampling, resizing, right? You have an image of 5 by 5. you wanted to fit an image of 25 by 25, just upsample it, resize it, right? Yeah, exactly. Interpolate, upsampling, perfect. Yeah, I see that you guys, yep, got it. So exactly, so we just upsample this feature maps, and we get them to the size of the input image, and then we just do the mapping, right? So far, what we have seen in this lecture are the following, right? So we've seen what is interpretability, what is the importance of interpretability, the scope of interpretability. We've seen the 5 different levels of interpreting a model. We've seen what are the simply, easily interpretable models, and we've seen LIME for both tabular, text, and image data. And then we've seen GradCam as a very good algorithm for explaining convolutional neural networks decisions. Again, this was just the this should have been an example of how to use upsampled heat maps, but for some reason the images are not loading. Let me try to refresh. Maybe the images will load again. Yeah, here they are. They loaded. So you can see. So this was the prediction or the heat map of GradCam, and then we just upsampled it to this matter, and there you go. So it's starting to give you something more in the size of the image. Instead of something of 12 by 12, became something of 500 or 45 or 450 by 45 or 450. And it's definitely very readable, right? The resources that I would recommend, highly recommend to read, Interpretable Machine Learning book. This is an amazing book. It's free. It's out there. And which one of these is very useful? Yeah, I'm gonna send you the second one, which is very useful. Of course, I used the variation of them, but there was one which explained it very well, and I think you guys should definitely check it. If you have any questions, please feel free to ask. And I think for now we will take a small break, and then we will go to the lab.
Yes, I've got a question regarding to the decision trees.
Yes.
Could you tell, please, how easily we can retrain or rebuild the decision tree according to the new data? Let's imagine a situation when you've got 10 classes, and after a few weeks, a customer come to you and say, hey, I want to have 12 classes. How easily we can rebuild the existing tree, or maybe it will be easy to build a new one?
1 second. So you just simply to answer this question, just look for the fit function. If there is a fit partial fit function, then it's doable. If there's no partial fit function, then it's not doable. Let's see, this is the parameters, attributes. Yes, there's no partial fit. So there's no, I think the best way to do it is to completely retrain from scratch. Because could be that the features that were used in the, so basically, for example, you started with 2 classes, and the feature A was very useful to separate them clearly. But then once you have like 10 classes, feature A is not the best thing you should start with. And these all, like the whole architecture of the tree can change if you add new data or you add new classes, especially if you add new classes. So retraining from scratch is definitely the best way you should do it.
Thanks.
Thank you. You guys, do you have any other questions?
Actually, no. But about like how the lab will take a long time or not? Like,
the lab, I will try to make it very short. So basically, it's a Colab link. I will go through it very quickly, just to, you already know everything there because it's everything we just described. And basically just see how it's done, right? Let me see, where is this Colab link? Is this close, stop sharing screen, share again, is this one? Huh. So there we go. So this is the lab. The different components of the lab are the following. Interpret by Microsoft is a very good library for ML interpretations, and it's very good for tabular data. So basically, if you'd like to explain anything regarding tabular data, you should always use Interpret Microsoft. It already comes with interpretable versions of different algorithms. So instead of using linear regression from sklearn and then trying to build an algorithm to interpret it and say this, for example, for using sklearn's decision trees, and then you just write the algorithm that traverses the tree back to the decision and how it was made. You can already find all of this implemented inside this library, use their decision trees, use their classifiers, their regressors. They're very, very powerful, and they give you interpretability out of the box, right? The second part would be to show you an example of how to use Lime for text and how to use Lime for image data. Very simple. You'll see it's very simple. GradCam also, it's super, super simple. All we have to do is just show it the model and it will do the training, right? First, a small tip, when you're installing, pip installing Interpret by Microsoft, you're going to have some problems in the beginning with the versions because Colab already comes with some libraries that are already in some versions that doesn't work with it. So only thing you have to do is just press this restart runtime button that will appear and run pip install again, and everything will work perfectly. Once it's installed, so basically we will take a variety of different examples here. Here we have a data set of, I'm not really sure, but this is for classification. So these are the columns: age, work class, education, and stuff like that. And we try to make some predictions, right? So here we have the training data distribution, 0 and plus. It gives you the distribution of the samples according to the class. So you can see, for example, we have a lot of positive samples for this one and not enough for this one. For this one, we have more orange and less blue, and so on and so forth. So this is very important to understand the distribution of your samples according to the category you are trying to make, right? I want to find something which is not categorical. Let's see, continuous. Yeah, continuous capital gain. There you go. Most of them are very small here. Let's see. Yeah, this is much better. So basically, this is just gives you a distribution of the values based on bins, right? Now we're using explainable classifiers. So they have explainable boosting classifier, logistic regression, classification tree, and decision list classifier. So there are a variety of these. You can simply train them as you would for a sklearn model using the fit function and then the evaluate function, right? And then you can easily explain global. So again, as you have seen, there are different types of explanations, different levels of explanations, and based on the global type of explanation or the local type of explanation, you will have a different type of report. So for example, if we come here, let's see something, the first one. No, this one. Yeah, this gives you the overall importance of the features in general. So for example, the age is most important, then this, then this, then this. So this is one way of interpreting your model. Then once you go to each and every, what is it called? Help me out. Each and every feature, it will start giving you the importance or the density of these. So basically, this is the distribution of the feature, and this is the error that it's making. So you can see here, when the distribution is dense, you don't make a lot of errors, but here we have this gray area of error. So this would just tell you that you are not doing very well on old people, for example, right? And yeah, this is one way of doing the predictions on a group, for example, understanding predictions on a group, or understanding how are the different features influencing the decisions, right? Yeah, this is local explanations, right? So let's take, for example, this one. And here it will tell you what were the features that contributed, right, to making the decision it made. Same thing again and again in different variations. Here we have the same ones, but for different models, so classification trees and stuff like that. And yep, sorry. So again, you can just play around with it. It does give you a lot of reports that are very useful for understanding your models, understanding your data, and explaining or interpreting these models. All of these, they're already interpretable models, so you can find more information in them. Now we will start working with what are they called? Black box models. Yeah, let's say it like this. So basically, they simulate the black box model by using PCA and then applying a random forest classifier, right? And then they use this to make the following. Let me see. Ooh, this one, right? So basically, we have our model, which is PCA followed by random forest classifier. So this is how we built it, right? We built the pipeline from sklearn, starts with PCA and then goes to random forest, and then we trained it. This is highly what is it called? So it's considered a black box that is not easily interpretable, but still we managed to understand the influence of these different values or these different features on the class. So this is positive influence, this is negative influence. So this is done using what? Lime. This is Lime on these data. There are other techniques. I think you should take a look on Morris sensitivity. We will not cover it, but it's very important. So I've used it in a couple of my researches, but it's not very important for our work right now. But definitely, if you're going to continue working, take a look at it.
About bug box, yes?
Yes.
Mm-hmm.
And yeah, these are just different. This is the same thing, but for regression instead of classification. There's a lot of stuff in here that are completely the same thing, but mapped into regression. Explaining black box regressors. Also, please do take a look at these. Take a look at the kind of reports that you will be getting, the names of the models that are the methods that are being used for generating these reports. And for now, let's get to our important part. So basically, Lime. To install Lime, so it's simple, pip install Lime, right? To work with the text data, we are using this data set of Fetch 20 news groups, right? So we have chosen atheism and Christianity as the two subclasses that we are interested in this big data set of 20 news groups. And we try to make a prediction on one of them. So this is basically just creating the model, right? So TF-IDF vectorizer, transform, and then we create a random forest classifier on top of the text, which is vectorized text. And we try to make the predictions on the text vectors, right? We calculate our F1 score, and the F1 score is very high, so this is good. Now, what does Lime give you? Just can somebody tell me again what is Lime working on mainly? So Lime, what does it give you? So what kind of interpretability does it give you? So far, we have seen in Interpret ML, it gives you stuff about the features in general, gives you stuff about the distributions, the stuff about the model itself, and then it gives you stuff about the predictions, about each prediction. What does Lime give you in this case? What are we supposed to ask from Lime right now? What should we expect from him?
Impact of each word in the sentence.
Perfect. This is a great what you said. So basically, we want to use Lime in here. So we have, there it is. So this is Lime text explainer. We give it the class names. Explain sentence. We give it the sentence. We have the predict proba and the number of features. 1 second. Yeah, this is, there it is. One second. Posting. Yeah, it's easy to see it in this in this one. So basically, we had the following text, right? This is our text that we submitted into Lime, and we asked Lime so we asked our model to classify it into either a Christian or an atheist text. And our model, I think, chose it to be a atheist text, right? And mainly we understood, well, mainly the reason why it was chosen as Christian, local explanation for class Christian. Yeah, so local explanation for class Christian, you can see that the model attributes the word university with Christianity, and attributes other terms such as .edu for the email, as with an atheist kind of word to put there. For example, in here, in this case, is considered as an atheist word. Host, NNTP, posting, all of these words are the ones that contributed to the model, to our model, to make the decision of being a atheist text, right? So mainly he focused on this area. So you can see NNTP, posting, host. These things are commonly found in atheist texts, apparently, and edu is also apparently found in atheist texts. But for example, the word university was linked to Christianity, mainly, maybe, for example, there are many Christian universities. So basically, it was easy to make this link between university and Christianity. So this is one way of interpreting the results on this long text based on the predictions of, or based on Lime interpretability, right? So this is
why, for example, this model haven't noticed what we have word Darwin, for example. Why not?
Oh yeah, sure. I mean, this is definitely Darwin should easily be the most important reason for it.
Yes, I don't know why. Why I haven't noticed.
For some reason, this could be a problem with Lime, because again, Lime is not perfect. So the method of Lime is not very perfect. Generating these random samples is not very perfect manner to do it. Or it could be just that your model isn't well trained. You see?
Maybe it's not normal. I mean, maybe because it was written in capitals. It not.
Could be. Yeah, it could be. So basically, right now, after you do Lime, you start your investigation. And you start saying, why didn't the model pick these things as important for our, because I think here Darwin's fish, this is kind of the most atheist words you can think of. So it should have picked these as the reason why it should have been classified as an atheist word, but it didn't. But that's okay, right? So now we're going to see how it's done on how Lime is used for images. Simply, we took this whole Mediterranean. So it's an image of a dog. We normalized it. We center crop, did a lot of stuff in here, just normalizations and stuff. Created our beautiful, used our beautiful ResNet from pre-trained model. This is very important. This is the JSON of the classes. Let's take a look at it. 0 trench, 1 goldfish, 2 a great white shark. So this is just to do the mapping between the output of the final layer and the name of the class, right? We were here. Next. This is just some code only because we are using a big data set, since we have the ImageNet with 10,000 with 1,000 class. So we had to use JSON to represent mapping from class index to class name. But if you're using a simple model or a simpler, what is called simpler data set with just 10 examples, you don't need to use a JSON to do the mapping. You can easily just make a dictionary like this. One is cat, for example, right? I am very horrible on this new laptop. Nice. So basically, you should just build a dictionary like this, and it will work just fine. Yeah, there you go. So we take the image. we transform the image. This is the important part, batch predictions. Now, in order for, what is it called, for Lime to work, it needs to be able to get the predictions of the different, I think it was here, no? Let me bring it back just so we can see them together. Where is it? Here. And the other one. This one? No, this one. This one. So again, what we need to give for Lime is the following. We give him what is the instance of interest, a way to perturb your dataset and black box predictions. So this is done by Lime on his own. So he will do the super pixeling and stuff like that. Weighting the samples, he will also take care of that with his own formulas. Now, this one is train the weighted interpretable model on a dataset with the variations. So basically, once Lime generates these random features, he should be able to get their class based on the algorithm, right? On the real algorithm. So all of these black points should will be sent to your model for classification, and then your model will give us the this probability class, or this probability vector, right? And then using this probability vector, we will be training the Lime. So here, batch predict is a very important function to write. It's the kind of the most important function you will be working with. And basically it takes a set of images, reads the images, sends them through the model, processes the logits, and then returns the probabilities in a NumPy format. So it's, again, it's a black box. So it doesn't really need to understand whether the model is written in TensorFlow or in PyTorch. All it needs is just a function. It sends the function a set of images, and the function would give it back a set of probabilities. And that's it, you guys. The rest is very simple. So basically, we create a Lime explainer. We use the explainer to explain the instance. So there you go. We give it the instance. We give it the classification functions. We give it how many labels should it focus on. Because if you have lots of labels, so for example, what we described in the course in here, so it's for binary predictions, right? For this one, you can choose how many labels will it be focusing on, and the number of random samples that are generated. So here, these black points, or for example, the different super pixelated variations, these perturbed instances. How many of these will be generated by Lime to make its predictions? And this is just for visualization purposes, right? So only thing you need for Lime is this line to call it, and the batch predict function, which is the black box model. You can think of it as the black box model that you get, right? And the TFSO. So basically, it said that this is the area that was used to generate or to explain the what are they called?
What's the dog?
Yeah, to generate the fact that this is a dog. This is just a simple amount of code that I just usually like to use for generating this. So basically, here's the dog. Here's the class that was mainly predicted. And here are the points or the areas which were used for making this prediction. Lime is very sensitive for the number of samples that you use. So for example, in here, we used 10,000. Look, the whole face of the dog was considered. But when I used only 100 samples, you see the results are not very optimistic. So you see it's only using the mouth and some of these areas. So always try to put as many samples as possible, right?
Could you please explain why in these cases there are so many different areas? For example, in the second case,
this one is just not well trained. So this is badly trained. So Lime did not train a good model yet. So basically, for example, what is it called? This one. Yeah, so we will be building a local weighted linear regression, logistic regression, right? But the problem is, if you don't put enough samples for this linear regression or this logistic regression, it's not going to be trained well. So basically,
understand.
Your performances will highly depend on how many samples will you send for the your logistic regression interpreter. Do you get it? You get why the difference between this?
Yeah, understand.
And
Thank
this.
you.
There is one thing you should guys focus on. Try to put a lot of these samples, but also the time. The time to generate this one was, you see, 1 minute 22. So if you're explaining just one image takes 1 minute 22, it's a lot of work, right? So that's kind of a bad reason why Lime is not very it's not very good for production. And now
if the model takes 1 minute to explain the image, then it's cheaper to hire a person who will do it.
Exactly, yeah. It would be cheaper to just have a person who looks at the image and just types back the class, yeah. So here we have GradCam, which is just a different approach. It doesn't use, for example, in here, we have 100 images that are being generated and then later fed into the CNN. So this takes a lot of time, consumes a lot of computational power. In this case, we're only calculating, we just send the image once through the CNN and we calculate the gradients. Calculating the gradients for one image is not very difficult. It's very fast, right? It's much faster than 100 images. So once we calculated the different gradients, we summarize them, and then we multiply the matrices with the weights and feed them through ReLU. So these operations don't take as much time as Lime. You will find here just a simple amount of code that implements GradCam. Just copy paste it. It's already out there and it works very well, right? All you have to do is, let me show you. Oh, it's not run. Let's run it then, I guess. Okay. And here we will see the difference between gradient guided backprop for GradCam and just GradCam on its own. The image, you cannot find the image. Let me see.
I think you have to run the whole notebook.
Yes, I will have to run from the start. Yeah, I mean, we have time. Till it's done, can you guys tell me any questions or anything you guys want to ask?
About maybe schedule.
This yes, this is very important.
The next Saturday, maybe we will start our lecture at 10 or at 9, if it's possible for you, of course.
I would really like it. For me, I am very aiming for postponing it a little bit further, because it's very difficult to wake up very early and teach for 3 hours and stay for 4 hours and a half and stay giving the best I can give you directly. So the problem is some of you always have meetings at 3 and at 2. So I would recommend maybe changing one session from today to either tomorrow or yesterday. So what do you think? So maybe we have 2 on Friday, 2 on Saturday, or 1 on Friday, 2 on Saturday, and 1 on Saturday.
On Friday, because Saturday, it's like a rest day for rest, relax.
Makes sense, yeah.
Yes, I agree.
Okay, so I guess we should just make a Telegram poll, right?
Yes.
Can you guys see Telegram?
Yep.
Nice. I will send you guys a Telegram poll quickly. And just tell me what you guys think. When are you free? How should we put it out? And we will organize it, right?
We're gonna have homework on this. Yeah.
I didn't.
Homework.
Yes, the homework. I will send you your first homework today. Hopefully after a couple of hours, it will be on Moodle, and you will have like 1 week. Sorry, to finish the assignment, and yeah, the quiz will be on next Friday at for the beginning of the lesson, and it's going to be very simple. So basically, the basics of what we have seen with convolutional neural networks and with interpretability. I will upload the lecture as soon as possible. So this lecture, I will just try to add, as we discussed, another graph for the scopes of interpretability, just to explain them better. And then I will upload it and upload the lecture videos also.
And another question about Microsoft Teams. We have to use it, or we can still use Zoom?
We can still use Zoom if one of you guys have Zoom Professional.
Or in other case, we have to switch off every 30 minutes, yeah?
Exactly, or we have to just switch off every 30 minutes. Sadly, the university decided not to pay for it anymore, since most of the courses are going back to be offline.
However, we can use a Skype.
Oh, Skype, yeah. I remember it. It's still working.
Yes.
Or Discord.
I am really down for Discord. Discord is pretty cool, but does it provide recording?
Also, Discord gives you only 720p quality. It cannot stream full HD.
Ah, okay, got you.
In the 1080.
Yeah, I got you.
So I think we should go. Also have 730, not 4K.
Yeah, I think we should just switch to Team and try it. If it doesn't work with Teams and we can find another solution, I might buy just 1 month. Or yeah, I think we have a 1 month course. I think I can easily just make a 1 month Zoom professional account and then just use that.
Do they have like this trial period?
I don't think so.
It's really funny.
Yeah, if they have it, I would create a new new one every year. Yeah, I don't think they have trial thingy. Yep. They don't have a trial period.
How long free session of Zoom?
Can you repeat, please?
How long is free session of Zoom? 1 hour?
Free session, 40 minutes, I think. They made it to 40 minutes. We can use Google Meets, but it doesn't provide recording. So basically, if we use Google Meets, I will use another recording algorithm, another recording software on the laptop and just go for it. What do you think? Is Google Meets worth it?
I think it's the same as Discord and Skype.
Yeah. I think we'll try Teams.
I think Teams also.
Well,
For first Teams, let's see.
Do you guys have any problems with Teams, maybe?
No, for now, no.
For now, no. Okay. So we can try it and see how it works. If it's not as good, I think one problem might be for the people who are free listeners. I'm not sure if they can access the university's Teams. So I'm going to have to speak with the university administration about this and see how can we fix this problem. Do you guys have any other questions, maybe, or?
Let's move to the lab. We didn't finish it.
Nice. So let's go back to the lab here. As you can imagine, what only thing you need to give to GradCam is your model, right? So here's model BGG19 pre-trained. The target layer name. So basically, which layer will you be using, or which? Let's go back here. Well, we said that we will be extracting feature maps from which layer. The algorithm that I found uses the final layer directly. This implementation uses any layer inside, as long as you just give the name of the layer, right? Use CUDA false. You can do this to just use only CPU or use only GPU. And then after this, take any image you want, process the image, and send it to GradCam. And there you go. This is your image. So GradCam, by default, the function saves this file to your local directory, and then you can just use this file here. You can see that there is a difference in the sizes, mainly because BGG19 takes images of this size and not like the input that we had. So again, as we said, GradCam, the way you guys will be using it is just 2 lines of code. It shouldn't be something that you should think about. It should be something that you should always be using. It doesn't matter what kind of model you do. Always verify it using GradCam. Preferably go to the samples which are mislabeled and just quickly look at the results, right?
And about target layer, why did you choose 35th layer? Because
why did I choose it? I didn't really choose it. So it was the layer that was chosen by default in here, and I think it was the final layer of final convolutional layer of.
But it's possible to choose any.
Yeah, let's try.
And the quality may be changed.
Different. Yeah, you might have a different output, right? So yeah, so definitely it's the final layer of CNNs, right? The next is linear models. Let's try 30, if it's possible, right? And see if it works. It worked. Let's see, how does it look like? Definitely a different output, you see? And that's mainly because the that layer is still not high level enough as the final layer. So the only reason why we use the final layer is because it's the highest level version of the model that we can get. We could go for Max Pooling's output. Let's see. I think Max Pooling's output would be even worse, since it does kind of remove some of the information from the image, but we can compare. And you can see it only takes a couple of seconds for image, and we are not only doing GradCam, we're also doing guided backprop value model, right?
Much better.
Much better even. Not bad. That's good. That's good news. So basically, this is the guided backpropagations, and when you combine the heat map over this one, you get this guided backprop GradCam, right? Guided GradCam. Only thing you should just focus on the name of the layers. Usually, in this case, they are numbered. In other cases, usually you will find them as just names, right? And there you go. This is how you use GradCam, by simply giving it the model, which activation maps he should be using, and then giving it the giving it the image, right?
Looks nice.
Yeah, it's very logical, very simple to use, and as I said, I highly recommend that you guys just take the code, put it in your in some files inside your repository, and create some module that just checks all the wrongly classified samples, and just visually try to see if the model is doing a good job, if maybe this misclassification was reasonable enough, or was the model not well trained. So this is another way of evaluating your model. Instead of using something just as simple as accuracy and F1 score, you can use such methods. Do you guys have any questions?
I think there is a question about homework. Which kind it's supposed to be?
It's going to be an easy homework, so you wouldn't really be surprised on the content. So simply you will be asked to create a simple convolutional neural network using PyTorch, and then sending this layer, sending this PyTorch to GradCamp and showing us some of the wrong values, what are their explanations, basically.
Got it. Thanks.
Yeah, it's pretty simple. It's going to be very easy to use and direct. I will put a poll soon. One for when should we move this third session, and the second one would be what are the topics that you want to cover the most. So for the first week, we went for very easy and well, introductory topics. I think that most of you already are familiar with many of the things that I've just described. So for the future lectures, it's going to be a bit more complicated, but I would say even simpler. So basically, these are like the basics, and that's why we spend some time with them like this. But like for the future lectures, we're just going to cover just the what are they called? So the intuitions, the architectures, and then how to use them directly. Although there will be new topics, they will be very easy if you already have the basics of what is encoder, what is decoder, what is overfitting, and all of these things. If you understand them clearly, you should feel very comfortable in the future lectures.
Thank you.
Thank you, guys. Thank you. If you have any questions, please feel free to ask right now, or else I think it's about the time that our friends would go for their meetings, right?
So there is a probability that we meet next Friday a bit earlier, yeah?
A Friday a bit earlier.
Yeah, because like if we agreed to add one more lecture to Friday.
Yeah, I mean, we could add it on Friday a bit earlier or Friday a bit later.
Oh, a bit later it will be, I think, too late because it will be
Yeah, for you
9.
guys, it will be too late.
As for me, I cannot take early.
I see. How about, yeah, I really don't see any. We will keep it this way for now and see about it after the poll. If we can't find any other location, I guess we will have to wake up early.
And the homework will be given for a week, yeah?
Yeah, I mean, I would give you for a week. For the homework, I would prefer if you give it back after 5 days. So I will set 2 types of deadlines. The first deadline is after 5 days, and the last deadline is after 7 days. So this is just a trick to get you guys to
do something.
To do something sooner, so that you don't feel the stress and the pressure of having a final deadline where you will not be able to submit after that. So basically, just a 5 days deadline. Try to submit over there. If you can't, it will be easier for you to continue working for the next 2 days. And it's just like a reminder, right? It's like an alarm for the homework.
Got it. Thanks.
Sure. If you have any other questions, please feel free to ask me right now or send me a message on Telegram. I'm always online usually.
Okay, thank you.
Thank you, guys. Have a great day.
Bye.
Bye-bye.
Have a good weekend.
So, Imad,
yeah,
as I wrote, could you recommend something in this area for research organization or LaTeX?
Let me share my screen and maybe we can see this overleaf. Yep. So this is the structure that I always use. Yes, let's use this one, for example. Let's go for yes. So I always use this one. So BibLaTeX, it's awesome. I just extract them, put them here, and then in the access text, so in the area where we are writing the paper, usually just add a simple command in here. Okay, just make it nice. So we just add these two commands in here, and it's pretty simple, right? So IEEE transaction, and then you send it where the file is. I find this to be much easier than using bib items, because bib items are like really difficult to maintain, and there's just like too much text inside this this file, and I like to keep this file as clean as possible.
So you use any extensions from Chrome?
Honestly, not really. I just go directly for just copy pasting from Google Scholar. Let's take, for example, this paper. Yeah, for example, like this. Yep. I don't know. How can you cite it here? Forgot. Okay. So for example, in this cases, just go to cite this and give text. In most cases, what I usually do is let's copy paste the text and search for it. It can't find it. Ah, this is profiles. Okay, sorry. Articles. Yeah, there you go. Here, you see these two quote marks? Just press on cite and bibtext. There you go. Take this, copy it, put it in your bib references.bib file. And that's it.
Also, I think about one project for computer vision.
Which is?
So, yeah, so I want to make application that measure concentration of people and use for it. Here's some research that's showing that people of human eye divide when they're using highly concentrated.
Okay, got you. So basically, you would like to, for example, inside a Zoom meeting like this, take the picture of the student at random times, and then find the eyes and find their pupils, right? Yeah, this could be a bit challenging, especially for people such as people with low quality cameras, or with people with black eyes, or even what they call maroon. The color of my background. This color is my background. The most common color of eyes. What is it called?
Brown.
Yeah, brown. Yeah, brown colors. Usually, it's very difficult to detect the difference between the brown and the black inside the eye. So it could be very challenging, but it's definitely interesting. Maybe like the quality of the cameras are definitely going to be increasing. And this is an area of research that you can just publish it. So even if it's not going to be a product directly, it can easily be a published paper. You know?
Yeah, I think it from which part to start. Find some that set of faces or eyes, or I'm not sure.
Yeah, for annotations, I would recommend using Supervisely. Let me share the screen again. If you want to do something really good, you should make your own data set, right? So basically, just take lots of images of eyes or of faces. Start with eyes first, detect the eyes. And then from the eyes detections, try to find or label the images of, so for example, like this. So try to label these rectangles. For you, in your case, you're trying to label the cycles. So basically use stuff like that. You know? Just for object detection, right? Yeah. And then define a simple ratio of, for example, the size of the pupil compared to the size of the eye thingy, and using that make your own algorithm.
Yeah, thank you.
Thank you.
Okay,
Okay,
goodbye.
guys. Bye-bye. Do you guys have any more questions? I think let's end the meeting.